Okay, so normally I handwrite my videos, but in this case I wanted to type it out because it's a bit of a tedious problem, but it can still be digested rather quickly, in my opinion. Okay, so the problem is, let's say you have 3 unbiased thermometer readings, T1, T2, and T3. Here, unbiased just means that, on average, the thermometers are going to give the accurate value, but whenever you measure it, there's going to be some random variation around the true value. And these measurement errors are going to be independent between the different thermometers. And that kind of makes sense. There's no reason one thermometer being off by a little bit is going to tell you how much off the other thermometer is. Okay, and then we can measure these with their variances, sigma 1 squared, sigma 2 squared, and sigma 3 squared, all of which are strictly greater than 0. So given this information, how do you minimize the expected squared difference from the true temperature mu? Or less technically, how do you combine these measurements in order to get the best possible prediction for the true temperature? Do you take the measurement corresponding to the most accurate thermometer? That might make sense, but ends up not being true. Would you take just the standard sample average? You weight all 3 measurements equally. In some cases that can be true, but in general it's not. So let's formulate this problem more mathematically so we can really answer it rigorously. So the examples on the last slide can both be expressed so that our guess is of this form, where we have a linear combination of the 3 temperatures. And this is a pretty standard thing where each weight is non-negative and the 3 weights add to 1. Then, subject to this constraint, we want to minimize this expression, where this is our guess and this is our average value. So we want to minimize the expected squared difference between our guess and our true value. So this is really why I wanted to type it out instead of write it out. This can be a little bit hairy, but here you can break this mu into each one of these parts, the T1, T2, T3, and that's what this line is. Now expressing the expectation of a square of a bunch of terms means you can do a double summation of these weighted terms, alpha I, alpha j, and then this expectation term right here. And this is actually simply equivalent to the covariance of Ti and Tj. Okay, so because we know this is 0 by the fact that they're independent for I not equal to j, that means those terms cancel, so we're left with the cases where j equals I, which ends up looking like this. Then writing alpha 3 as 1 minus alpha 1 minus alpha 2, we can get this very nice function of alpha 1 and alpha 2 that can allow us to try to optimize something very tractable. This is a relatively simple function in the land of optimization. So now we have to find the gradient vector and set it to 0 and all that business. So this is the first partial derivative with respect to alpha 1. This is the first partial derivative with respect to alpha 2. And remember, we don't have this term for alpha 3 since it depends on alpha 1 and alpha 2 completely because of our constraint. Now setting this equal to 0 and solving algebraically, we can get alpha 1 in terms of alpha 3 times this constant, and then alpha 2 in terms of alpha 3 times this constant. And then because we know that alpha 1 plus alpha 2 plus alpha 3 equals 1, now we have basically alpha 3 times this constant, sigma 3 squared over sigma 1 squared, plus alpha 3 times sigma 3 squared over sigma 2 squared, plus alpha 3 equals 1. We very nicely have an expression where we can factor out alpha from here. See if I can pretend to do it here. There we go. And essentially get that alpha 3 is this value. And that looks pretty ugly, but we can rewrite it in this visually appealing form. Alpha 3 equals 1 over sigma 3 squared, and then with this normalization term that you see throughout both these terms. You can also find alpha 1 and alpha 2 just from these equations we have here. And there we go. We see that each alpha I is proportional to 1 over sigma I squared. But then there's this normalization term, which is actually called the harmonic mean, that allows these things to be, or to sum to 1. The harmonic mean specifically of the variances. Yeah. Okay, and then technically you have to check the Hessian too. And if the Hessian is positive definite, then you know you've found a local minimum here. And I'll leave the fact that this Hessian matrix is positive definite. I'll leave that as an exercise to the viewer if anyone really wants to do that, but it's not too bad. So, anyways, now we know that this solution of alpha I being proportional to 1 over sigma I squared is optimal. Now let's just take a tangible example. Let's say we have 3 measurements. So T1 would be 74 degrees, T2 is 76 degrees, and T3 is 79 degrees. And they're corresponding to variances 1, 2, and 4. Then our weights are 4 over 7, 2 over 7, 1 over 7. And then our guess is this linear combination of them, which ends up being around 75.29 degrees Fahrenheit. Here, I'll just address a couple practical considerations. So the assumptions of your thermometer as being unbiased measurement tools, that alone is a little bit unrealistic and hard to verify without just extensive statistical tests and whatnot. And having constant measurement error over the range of values being measured or over some arbitrary true temperature, that's also unrealistic. That's even hard to verify statistically, trying to show homoscedasticity of, showing variance is constant throughout the whole range. But that said, this procedure is really good enough, a good enough framework to combine different measurements rather than just picking the most accurate thermometer or the most accurate measurement device and just using that one. Because if you have independent measurements, no matter how bad the other values are, so long as the variance is finite, you can use it to your advantage to improve the prediction of your measurement. Now, thank you for listening, and hope you have a good day.